Okay, everyone, so let's get started. So this is lecture 15, and this week really starts our transition away from using the Arduino Uno and just using a bare ATmega chip, factory fresh chip on a breadboard, and we have to provision that with various support circuits to make it work. So today what I'm going to do is I'm going to walk you through a very sort of detailed step-by-step, wire-by-wire step for how to build what you see there on the left side of the screen. And what I'm going to do is really just follow a detailed memo that I've posted to this week's Moodle tab. So you can follow along with the lecture slides here or with that memo. And it'll take you step by step through it. The other thing that's going on right now is I have assigned lab assignment number 4, and it is not as complicated as the previous one, the one that you just sent in, the thermometer. The assignment is to make a variable speed motor controller, and the idea is just a couple buttons, 2 different buttons. And between those 2 buttons, you're going to have 4 different speeds of a motor. The issues are that you have to hook up a motor to the Arduino, to the ATmega chip, and the GPIO pins on the chip don't provide enough current to drive a motor. So you need to use a transistor. You have that in the kit. I'll show you how to do it. And then, the output of an Arduino, of this, I keep saying Arduino, the output of the ATmega chip is either high or low. It's a digital output. So the question is, how do we get variable speed to a motor? We use something called pulse width modulation, and so that's what we're going to be introducing. So the new peripheral that we'll be introducing in conjunction with lab assignment 4 is called the timer counter, and I'll describe that on Wednesday. And then on Monday of next week, a week from today, we'll sort of go down in detail and I'll show you how to use the transistor and how to use pulse width modulation to connect a motor. And so I'll be giving you nearly all of what you need to do the assignment. But there's an awful lot of bits and pieces to it primarily because we're coming off of the Arduino Uno board and we're kind of, in a sense, building up our own Arduino Uno board from scratch. So there's a lot of bits and pieces to it, and that's where the complexity comes about. A week from Wednesday, we will have a Q&A for lab assignment number 4. So come to class if you want, don't if you don't have any Q&A. After that Q&A, I will publish just a tutorial or a couple of pages of design tips for lab assignment number 4 to Moodle, so be on the lookout for that. Then this assignment, I was originally going to make this assignment due 2 weeks from today. That's Patriots Day holiday. I am aware that when I make an assignment due on a Sunday, it causes a fair amount of frustration for many of you who want TA support in the days before the lab is due. So what I'm doing is I'm making this one due 2.5 weeks from now. So it'll be really due 2 weeks from Thursday. That way you do have 2 weeks plus then a couple more days where the lab is open and you have access to the TAs. But I implore you not to wait until 2 weeks to start this. There's just too many bits and pieces to it. And so the assignment, it's posted now, and you'll see that it actually asks you to do 2 things. One is to replicate everything we're going to do today. Just replicate for yourself everything that we're doing, and that'll run you through end to end to get you to the point where you can build up a circuit with a bare chip on a breadboard with all the additional circuitry that are needed, and you can get flash code to it. So that's the first assignment. Nothing to turn in there, but I want to make sure you can do it. And the second assignment is this motor controller. All right, so more on that as time develops. So what I'm going to do here is just walk you through how do we kind of remove the training wheels, as it were. We've been writing real C code on this chip, but the chip has been on an Arduino Uno. And so now we do away with the Arduino Uno and we just use the bare chip. and how do we make it do what we want, okay? So what I've got here on the left is kind of a drawing, or a sort of a sketch of the Arduino Uno, and it shows you the various things that are on there, the various boxes that are in yellow. And what we're now doing is we're just taking one of those boxes, the ATmega328p chip, and we're just going to build up our own circuit out of that. So one of the things that we're going to have to do at this point is start to really get more accustomed to looking at the various pin designations on the chip itself. We're done sort of talking about Arduino pin 1, Arduino pin 2, and we're going to be focusing more on the chips associated with the ATmega, the pins associated with the ATmega itself. So just some things that we have to be aware of. So we've been working with the ATmega chip built into the Arduino Uno, and we're going to be using a factory fresh ATmega 328p chip. You've got one in your kit, and it's on a little piece of conducting foam. Now, the chip that's inside the Arduino Uno has a couple things that your factory fresh chip doesn't have. One, it's got what's called a fuse. It's set for an external 16 megahertz clock. And so the fuse is something inside. There are 3 fuses inside the ATmega chip, and these are non-volatile. And what that means is that once they have a certain value in them, those values stay there, even when you power down the chip, when you erase the chip, and when you reset the chip. You set these fuses, and what they do is they set some configurations about the chip. And so one of the fuses on the chip in the Arduino board has it using an external 16 megahertz clock. And so if you look down on the Arduino circuit board, there's an external clock circuit down here. It has a crystal and then a couple capacitors. And so that little circuit creates a square wave at 16 megahertz, 16 million cycles per second, and that provides a clock for the 328p chip. When you get a brand new chip from the factory, when it shows up from the factory, then it's factory set with its fuse using an internal 1 megahertz clock. Okay, so it's set to look for an internal clock rather than an external clock. Now, there's nothing necessarily wrong with that. It means it runs slower, and so some programs would run a little slow. We wouldn't really notice it for what we're doing. But the main issue with that is that a lot of the code that we're going to be developing, we've developed some already using the UART, but it makes use of timing. It has certain baud rates, and there are certain things where we've assumed a 16 megahertz crystal, and we've divided some things down to get certain optimal rates. They're sort of buried in the code, but we've been assuming a 16 megahertz clock. So one of the things that we're going to need to do is change that fuse so that we configure that chip to use an external clock instead of an internal clock. Okay, that's not a big deal. Also, the chip on the Arduino Uno has something called a bootloader code in it. That's a little piece of code that is taking up part of the flash ROM, and that allows the chip to be programmed over the serial port. Now, that's kind of a non-standard way of programming one of these AVR microcontrollers. Normally, you get one of these chips, and you don't have this bootloader code occupying part of your flash ROM because you want all that flash ROM available for your code. And so when you get a brand new chip, it's empty. It doesn't have that bootloader in it. It doesn't have that special code that kind of allows it to boot up on its own and take a program from the serial port. So instead, we're going to program it over what's called the serial programming interface. Now, this is actually the standard way, sort of the grown-up way of programming one of these chips. Using a bootloader is really not the standard way of programming it. So more on that later on. So that's just a little bit about differences in the chip that we have to be aware of. Now, when you have that chip on the Arduino Uno board, the board is providing the 16 megahertz oscillator. We talked about that. It's also providing 5-volt power supply. The chip, the 328p chip, can work with as low a voltage as low as 1.5 volts if you're running it at a low speed, up to about 5.5 volts. Under no circumstances can you go above 6 volts with it. You can damage the chip. And so 5 volts is a sort of is a standard voltage to operate this chip at. And some of the other devices that we have, like the sonar and this organic LED display, they use 5 volts. So because of all that, we're going to use 5 volts to power the chip. And on the Arduino Uno, there are various ways of getting 5 volts. You can take it directly from the USB cable, because the USB standard is a 5 volt standard. So when you plug the Arduino Uno into your computer, it's getting 5 volts off of USB. But then there are also various other ways that you can power up an Arduino Uno with voltage regulators and things. And so we have to be aware of that, and we just have to provide 5 volts power to power up the chip. Whoop. Okay. The other thing is, well, we're going to need something called an external programmer to actually program the device. Since we won't programming it over a serial port, we're going to program it over the serial program interface. Later on, when we want to do stuff with the UART, we're going to need an external serial to USB converter, because there's one of those built onto the Arduino Uno board. Okay, so a lot of the stuff that we just sort of take advantage because it's already there on the Arduino Uno board is not there on the bare chip, and we'll just have to provision all that. That's all, and you've got it all in your kit. So this is where we're going. If you sort of look at the minimalist circuit with the essentials, it's not really all that complicated. You have to power it up with a 5 volt supply, and that's just going to go to pins 7 and 8. We're going to put a crystal and a couple capacitors on it so that we can get the external crystal. That'll give it its time base. And then when we want to put code on it, well, of course, we'll start out with your host computer, and we're compiling it with make, and then when we do make flash, that's actually running a program called AVRdude, AVR downloader, uploader. And then what we'll be doing is we'll be connecting it to this thing called the AVR programmer. It's in your kit. And then that is going to connect to the chip using something called a 6-wire serial programming interface, or SPI. And so this is a standard programming interface for connecting a programmer to the chip. Now let me just sort of hold up what one of these things looks like. I'm actually working on a circuit right now, and I'll hold it up to the camera. It's a pretty busy circuit. It has a little buzzer on it, and it has this organic LED display, and I'm programming it using this. This is it's called a pocket programmer, but that's the device back over here. That's this device here. And so that's the device that serves as an interface between the chip itself and your host computer. And I'll show you how to configure this. But the standard interface there is called SPI, Serial Programming Interface. So I just want to say a little bit about that. Well, first, let me just show you an example of that. Now, the one that I just held up was this little red one here that you've got in your kit. Okay. That's one example of a serial programmer. It's kind of slow. You'll notice that when you're downloading code using this, it'll take a little bit. I mean, seconds, not minutes. But there's another version of that called the Atmel Ice. That's this white box on here. They cost more, and so they're kind of costly enough that it was prohibitive of us to give one of those for you to keep in your kits. So that's why we went with the pocket programmer, the red one instead. But I just wanted to show you a video that you've seen before in this class to flash some code to the chip on a breadboard. Okay, so I'm just going to go, and I've got a little movie here. It doesn't do much, but let's see. Let's run it. Okay, now you can't. It's downloading code, and all the code does is it blinks that LED. Now I can pull away the SPI interface and the programmer, and the code is now embedded on the chip. Okay, it's in the flash ROM on the chip, so it's non-volatile. I can power it down, take the power away. That code has been flashed to the ROM on the chip. And in this case, I'm powering it up with a 9-volt battery, and we'll be doing that. I'll show you how to get to that today. Some of the there are some capacitors in some places and capacitors missing in different places in this particular circuit shown here. So as I've just sort of shown on the bottom, I just wanted to give you this as an illustration of where we're headed. The actual circuit that you're going to build looks slightly different from this, but I wanted to show you this as an example. Okay, so just to back it up, you're gonna get your code. You're gonna compile it using you compile it using AVRGCC, and then you download it using AVRdude. Both of those things are taken care of for you in the make file. So you type make or make flash, and that'll compile and then download. And then once you're done, you no longer need to have the programmer. You just take it out of the picture. Okay. So I've got a question. Can the Pocket programmer be used for other microcontrollers like the ATtiny? Yes, it can. You can use that Pocket programmer for many of the chips in the AVR series. I don't think it can program some of the real big ones, though. Okay, so let's get going. How do we do it? Well, you're going to take your chip out of your little red parts bag. It's on a piece of foam. You want to be careful not to give the chip any static electricity. So sit down, touch a piece of metal first. Kind of ground yourself. Give yourself the shock if you have to. What you don't want to do is on a dry day walk across a carpet, pick up some static electricity, and then touch the chip, because you could damage it, right? So when you sit down, just touch a piece of metal, so that if you have any static discharge, it'll run through the metal rather than the chip. Okay, you pick up the chip, and then the first thing you do is we want you to plug it into the solderless breadboard. So you're going to plug it into that breadboard. Now, right out of the package, the wires on these chip are always too wide to fit into the breadboard. The pins are just too far apart to actually straddle and fit into the sockets on the breadboard. So what you have to do is kind of bend the pins in a little bit. So you just take the chip in your hand, and you take all the pins at once, and you just press it gently against a hard surface, and that'll bend the pins in a little. Then you flip it over and do it on the other side. Okay, don't be afraid of it. Just you have to do that in order to fit it into the chip, to fit it into the breadboard. So you do that, and then you wire up power and ground, by which I mean VCC, the red wire, which is going to be 5 volts, and ground. And you want to do that. It's pins 7 and 8. So we're going to get used to looking at the pin diagram here. VCC is pin 7, and that's this one here. And you see I have a red wire connecting to a VCC rail on the breadboard, and then I have a black wire connecting to the ground rail on the breadboard. Okay, and I've just indicated the pin numbers. This is the 28-pin chip. It's actually called a 28-pin DIP for dual inline package. Dual inline package just refers to the fact that all of the pins are in line. They're in a row, and we have 2 rows. Okay, dual inline package, as distinct from a quad flat package, which has 4 rows of chips and doesn't fit into a breadboard. If you're ever trying to figure out which is pin 1 on the chip, you just look for the notch or the dimple. There's a notch up here, or there's a dimple, but there's something up there, and just to the left of that will be pin 1. So that's how you know where is pin 1. Look for that notch or dimple. Okay, and then that's pin 1 down to the end. That's pin 14. It says 14. On the other side, it's pin 15 and then 28. Okay. Okay. Now I just want to say a little bit more detail about this serial programming interface. Nothing to be intimidated by, but it's a 6-wire interface. And I've drawn it in a couple different ways. This is the way you just saw it in a previous thing where I had the animation. So you have it's called a programmer tool or an external programmer, but that's that device that sits between your computer and the chip, and it interfaces over the serial programming interface, SPI interface, which has 6 wires. And the wires are reset, ground, system clock, MISO, MOSI, and VCC. And here I've just identified where they all are. There's reset. See, one of the functions of that chip is reset, and there are VCC and ground. Okay, then there's system clock, and then there's MISO, and then there's MOSI. Okay, And then I've just given them the names over here, okay? System clock, MISO, and MOSI. Now, when I talk about it, I'm going to use the term main out, for MISO, main in, secondary out, and for MOSI is main out, secondary in. We don't have to get into the details of this protocol. It's just a matter of knowing which one is MISO and which one is MOSI. Now, just for your information, a number of us have taken to calling these chips something like main in, secondary out. So we're using main and secondary. If you look in a lot of the documentation, including the documentation for the chip provided by Microsource, they actually use the terminology master and slave. So MISO refers to main, master input, slave output. Why they continue to use that obviously oppressive metaphor for this is beyond me. But it exists in a lot of the literature in technology. I've asked, and a number of people have asked Microchip to change it, and when they're going to change it, no answer from them yet. But just know that that's an issue, and we're using different terminology because there's just no need for us to use a metaphor like that for this. You'll also sometimes see this interface shown this way, and I'll show you why that's the case. But all that's important for us right now is you have these 6 wires. Each one has this function, and I'm going to show you where to connect them. Okay. So with your Pocket Programmer, there's also this flat cable. You just plug one end of the cable right onto the Pocket Programmer. And there's a little notch on there, so it can't go in backward. It's sort of keyed. It only goes in one way. Then the other end of that programmer, it actually has this open connector, and that's what this looks like. Okay? And it also has a little notch on it, and so you can locate the notch so that you can orient it, because otherwise the question is it, does it go this way or this way? And then once you locate the notch, you know where the various pins are: VCC, MOSI, ground, MISO, system clock, and reset. So now what you're going to do is later on, I'm going to show you how well, maybe I can show it to you right now with this little, I can hold this up to the camera if we can see that. So here I have this cable, and it's connected to a socket, a connector that I have on my board. And I'm just going to pull it off of that board, and you can see I have this, if I can focus on it, that's a socket. It's called an ICSP, in-circuit serial programming connector. And this cable is designed to match with one of those sockets on your circuit. And when you make a printed circuit board, as I'll show you in the last slide today, very often when building an embedded system that's going to go installed somewhere, the designers will put one of these sockets right on the breadboard, right on the final printed circuit board. So if they ever need to reprogram the chip, they can take this flat cable, plug it into that socket. It's a little tricky to get a socket like that on your breadboard, and I'll show you why that's the case. So what we're going to do instead, at least initially, is instead of having a socket that will sort of mate with this, what you're going to do is just grab 6 wires and then insert the pins of all the wires into this socket. And then you'll just wire them. Here are the detailed instructions: 1, 2, 3, 4, 5, 6. You just wire those to the appropriate pins on the ATmega chip. Okay, so you just insert 6 wires in there. You can use any colors that you want for the wires, as long as you use red for VCC and black for ground, and then you can use any other colors. Whenever I do this, I always have a certain color code that I use. I use red for VCC, ground for black, and then I use yellow for MOSI, green for MISO, white for system clock, and blue for reset. I never have to think about it. I grab the cable, and I've got these colors. I know what they are, and that consistency just makes it easier for me to connect and disconnect. And the reason why I say connect and disconnect is, you look at the picture on the left, the lower left, you've got I've got the cable connected to the board. Once you flash some code, you want to pull the programmer away, so you're taking all these 6 wires out. Not a big deal to connect them, but it takes a minute or so to do it. And so if you always stick to the same colors, it makes it easy. Is there a question there?
In the back? How do you know when it's done flashing?
How do you know when it is done flashing?
Then AVRdude will tell you. Put another way, when you type make flash, the last thing that make flash will do is it will run AVRdude, which is a piece of software, and it will go through and it'll say, I'm reading the chip, I'm doing this, I'm done, thank you. And it's quite polite, it says thank you. So it's what you've been seeing all along when you've been invoking make flash to download code to the Arduino. It's going to look exactly the same. So that program will tell you that it's done, and it'll say thank you. And if it was unable to flash, it'll say error. And I'll show you an example of that in a little bit. Okay. Moving along, I'm going to show you an example here where we just do the sort of the hello world thing. We're just going to connect an LED to one of the pins and make it blink. So I'm just suggesting in this little tutorial, connect it to PB5. That's the pin that on the Arduino Uno corresponded to the internal LED. We don't have an internal LED here because that context doesn't make sense, the idea of internal to the board. But we're just going to connect an LED to that, okay? So there it is. Whoop. Go back to the circuit here. I've got my LED is the green LED. There's the current limiting resistor. And I've actually got it plugged into this pin over here, which corresponds to PB5, which you can just get from the pinout drawing. Okay, so once that's all done, let's go ahead and plug the Pocket Programmer into the computer using the USB mini cable. You've got 2 of those cables in your kit. And as soon as you do that, you'll notice a bunch of things that light up on the programmer. It's getting power from USB, right? And it's actually powering up the chip. So now we're sort of ready to go here, right? All those little LEDs glow on the Pocket Programmer. Now, one sort of strange thing about this is that this programmer, when connected through USB, will provide 5 volts to power your chip. That's a good thing. It has a switch on it that is supposed to be able to switch that power on or off. And it's convenient to be able to switch it off because later on, we're going to have a voltage regulator on the breadboard powered up by a 9-volt battery. And we don't want to have both of those things providing power at the same time. So there is this on-off switch on this board. On mine, I took it out of my kit, just like yours, new thing, I took it out of the kit, and that switch doesn't work. It doesn't actually shut off the power. And I went and did some Googling, and I'm finding a number of people saying that the switches don't work to shut off power. It's not a big problem for us, but it's just something to be aware of, and I'll tell you more about it later on. Okay, so we've got this Pocket Programmer set up. All these wires here represent our 6-wire serial programming interface. We've got an LED. We're going to write some code to blink the LED and flash it. Okay, if you're using Windows, and you Windows users are accustomed to this, you have to get a driver. So you go to the SparkFun website, and they will point you, they'll give you the instructions, and they'll tell you where to go to get the driver that you need so that your computer can talk to this device. Okay, if you're using Mac, you don't need a driver. Okay, but I went through this using Windows on a virtual machine on my laptop, and it worked out just fine. So once you've got the driver done, you now have this device is seen, that is the Pocket Programmer is seen and recognized by your Windows operating system. So the very next thing we're going to do is we want to issue a command to the chip, or to the programmer and the chip, just to make sure that everything is connected right. So what we're going to do first is verify that the programmer is able to communicate with the chip. All right, we want to know, can the programmer talk to the chip? Okay, and we're going to type this command, AVRdude. That AVRdude is the piece of code that actually downloads your binary file or your hex file after it's been compiled to the chip. And we've been using this for weeks. It's just that we use AVRdude embedded in that make file, because the make file, it really just automates all this for us. But what we're going to do is we're going to type AVRdude, and then the programmer is called USB Tiny. That's this little red program. Its name in sort of, you know, AVR jargon is USB Tiny. And then P ATmega328p, that just specifies the chip. So you're just going to type this, and this is either you'll do this from terminal or from command prompt if you're on, you know, Mac or Windows respectively. Okay, and then AVRdude will respond. So here it is. I'm just showing you this on my Mac. I just type AVRdude space hyphen little c USB Tiny space lowercase p and the chip number. So I've just specified the type of programmer and the type of chip. AVRdude says, okay, your device is initialized, ready to accept instructions. And then AVRdude reads back a device signature. This is a signature on the chip that gets read back by the programmer in AVRdude. And it's got this number here, 0x1E950F. That indicates that it's a 328p. So AVRdude says, yes, I see you, and you're probably a 328p microcontroller. And then it says you're done and thank you. Okay, now when I do this on my Mac, it also reads back these fuses. Okay, and I mentioned briefly what the fuses are. I'm going to say more about them. On the next screen, I'm going to show you what this dialog looks like when I do the same thing on my Windows. Okay, it just doesn't read back those fuses. It's not critical, right? But here it is. Here it is when I do precisely the same thing on a command prompt on Windows. So I did that same instruction. I invoked AVRdude with those two parameters, and it's happily, it says the device is initialized, ready to accept instructions. Here's the device signature. The fuses are okay. Thank you. We're good. So now we know end to end, we're happy. The computer's happy with its driver. We've got the programmer. It's connected correctly to the chip. The chip has power, and we've got communication all the way through. Okay, so now I want to talk about fuses. Okay, so what we're going to do is we're going to read the lower fuse setting, and the situation here is, I mean, there are too many words there, right? What I did is I just copied directly everything that's in the memo that I've got for you to read. But let me just tell you the deal here. So there are 3 8-bit fuses inside the 328p chip, and they configure all kinds of things. They configure something called a debug wire, whether or not you can use the reset wire. Those fuses will configure whether or not you can program this thing, reprogram it. Once it's been programmed, you can change a fuse so it cannot be reprogrammed. You can understand why you would want to do that. You may not want someone to change the flash ROM on the chip. But of course, once you set that fuse, preventing it from being reprogrammed, you're not going to reprogram it again. And so there are a number of ways, if you're not careful, to set the fuses on the chip and render it unusable. You can brick one of these chips so that you just can't use it again because you get yourself locked out. We're not going to do anything that's going to get us into that kind of trouble. But what we want to do is we just want to read the lowermost fuse. There are 3 positions. There's an upper byte, an intermediate byte, and a lower byte. And we just want to read the lower one, and we just want to see what the value is, and we want to make sure it has a value appropriate for using an external clock rather than an internal clock. Now, why is this? It's perfectly valid to, when you get a brand new chip, factory fresh chip, take it out of the package, it's got its fuse programmed to use an internal clock. It generates its own internal clock. It's actually 8 megahertz. It divides it down by 8, and it operates at 1 megahertz. It's perfectly fine to use that. But you may want to use code that you already developed for your 16 megahertz application. And so rather than keep track of 16 megahertz code and 1 megahertz code, and there are ways of doing that, but rather than do that complexity, what I'm recommending is that everyone change the fuse setting so that this brand new chip will be configured to accept an external clock, and that's fine. The thing about this is you have to, before you do this, you have to actually put an external clock on the circuit. You don't do that, you brick it. It becomes non-usable. Okay, so what I want you to do when I say all this is I want you to have a healthy respect for the fact that setting fuses the wrong way can render your chip unusable. Have that as a healthy respect, but don't be afraid of it. If you break the chip, we'll get you a new one. So don't be afraid of it, but just respect the issue of the fuses. Okay. So here's the command we're going to use. You'll recognize this from before. We're just going to specify all this. What this will do is it will just read the lower fuse setting and print it on the screen for us. Okay. And so here I go ahead and do that. Here's that command. And I know I'm going by fast. I just want to show you the steps. You'll see all of this detailed in the memo that I've got posted. But when I go and do this, it says, okay, we're happy. I'm reading the fuse, and then it gives it to us. That lower fuse setting is 0x62, text value 62. If you were to go to the data sheet and look it up, 0x62 corresponds to internal 1 megahertz clock. That's all. And same thing if you did it on Windows, right? If there's the dialog there and you'll get the same thing. So what we want to do is change it from an internal clock to an external clock. And so that's what we're going to do next. Okay. So I'm going to walk you through how to do that. So the first thing you want to do before we change it, before we tell it that it's going to use an external clock, we have to give the circuit an external clock. So you picked up a little red bag, and it has these capacitors. They're 22 picofarad capacitors. They actually have 22 written on them. You also have this crystal that was in the first red bag when you picked up your kit. And you just want to build that little circuit right here like this. It just goes between pins 9 and 10. It's a simple enough circuit. You need both the crystal and the capacitors to make this circuit work, and that will provide a 16 megahertz clock for the chip. Okay, and you can see it on the right. I've just added those devices there. Do this, build this circuit before you change the fuse setting. That's all. Okay, so now we have that new chip. Its fuse is set for an internal clock. We're adding the external clock. Do you need the LED? No, the LED is just there for an application. Where I'm headed is I'm going to make that LED blink. You don't need it there, but that's the particular app that I'm going to put on here first. Okay. See, what we're really doing here is we're building up to an Arduino, something like the functionality of an Arduino Uno board. All right, this thing here, and recall that has an internal LED on pin 13, which corresponds to PB5. Well, this LED is the same thing. So you could use the same blink code that you used before to blink the LED on the Arduino Uno, but we're just building up our own, right? And think about it. Every single one of you surely wants to be able to build your own, version of an Arduino Uno instead of having to rely on a device that was made primarily for artists and hackers and things like that, right? So it's important to know how to do this. Okay, so you've got that circuit on there. It's not hard. Now we're going to change the fuse. And all we're going to do is type this line here. AVRdude, USB Tiny, you've seen that before. And instead of reading a fuse, we're writing a fuse. That W means write. And we're writing 0xFF. So when you type that command, all that will do is it will read that, it'll change that fuse setting. That's it. And once you've done this, you'll know it worked because it'll say thank you, right? It's happy. And we've now changed the fuse setting on the device so that it now uses that external clock. Okay. Okay. We've got our chip powered up. We've got the serial programming interface. We've got the clock set, the fuse set. We've got our LED on there. Let's get some code now to make the LED blink. So just get your blink code. I mean, this was the very first thing that you wrote. Just code to toggle or an LED on PB5 on and off. Okay, so we don't have to, no elaboration is needed for that. You have to change the make file a little bit. The previous make file used the Arduino as a programmer, and it used a serial port. Now we're using this USB, a tiny programmer, and we're using USB port. So there are some things that are different about it. So I've created a new make file, and I've posted it to this week's Moodle tab. So just use this one instead. So you know how you always have to have a make file in your project directory, and you always have to change the name of the source code file, right? Well, in this one, that's the only thing you'll need to change. So every time you want to compile and then flash code, just change the name of the source code file, use this make file, and that will flash it to the device using this programmer that we've got. Okay, so let me go ahead and do it. I've got that make file in the same directory as the source code file. I'm just going to type make, and it's going to go and do all of this stuff. All right, it's checking all that. Then I'll do make flash, and it does all of that kind of stuff, and it says thank you, and it's flashed the code. And so here it is. You can see the LED flashing. So what we've done is built our own Arduino Uno in a sense. Okay, we powered it up. It's getting its power from the USB on my laptop. Now, in an embedded application, obviously you're not carrying around the laptop. So a question, do we have to delete the ELF and hex files? No, you don't have to. You don't have to delete those when you change the source file. That's taken care of automatically. So I just want to show you different ways of powering this chip. Okay, you can see right now we're powering it via the Pocket programmer, right? So this programmer is getting power from USB. A couple other ways of doing it. You can power the chip directly from USB. The USB standard is based on a 5-volt power supply. So inside a USB connector, you've got 5 volts and ground. You've got a cable like this in your kit. It plugs into a USB adapter, and then it just gives you alligator clips on the other end. So you can take that and you can connect the red to your voltage rail, the black to your ground rail, and you're using USB power either from your laptop or you can plug it into the wall, okay? And you can power the device that way. So you have this cable, you have the little wall adapter in your kit. This is a way of powering this thing from without once it's been programmed, you just have to give it power. So you'll find this to be a convenient way of doing it. Okay. I'm going to show you one additional way if you wanted to go portable. How can you power this if you don't have a USB power supply around? Well, you can use a 9-volt battery. You've got that in your kit. And the key is that we're going to use a voltage regulator. So this is called a 7805 linear 5-volt regulator. And you've got your V in and ground. That's going to be, for your 9-volt battery, V in and ground. And then you're going to get V out and ground, same ground, you're going to get 5 volts. So this device will take in, it'll actually take in a wide range of input voltages between 7 and 17, and it'll give you 5 volts plus or minus a small deviation. So it gives you a relatively clean output voltage of 5 volts, and you can use that to power up the chip. Okay, and so when you do the homework assignment where you've got a motor, your circuit's going to look a lot like this. The additional devices are going to be a couple of switches, a transistor to drive the motor, and an RGB LED, and then the motor. Okay, all right. Just sort of the note that I have there in red. So when you do connect back your Pocket programmer, disconnect the 9-volt battery. Okay, and also if you don't want to drain the 9-volt battery, disconnect it from the circuit, because as long as it's connected to the circuit, it's going to be powering the circuit and it'll drain the battery. Okay, the very last thing I wanted to show you is, and this is just some optional stuff, and then we're done unless you have questions. I just want to show you 2 tips that could make your your life a little easier. You're going to have to be connecting and disconnecting this 6-wire SPI interface. And so what you don't want to do every single time is go and start grabbing 6 wires from your kit, plugging them into the socket and rebuild it. So you've got 6 wires, make a bundle out of it. Just put some tape around it, right? And keep it think about this as a tool, as a 6-wire bundle. Keep it connected into this socket, right? Remember what colors you chose for what wires. Then every time you want to program it, you're just going to pick up this reference that you make, and you'll just be able to plug it back in to the right places on the chip. You'll save yourself time when you do that, rather than every single time returning all these wires back to your pile of wires. The other thing that you can do, if you wanted to sort of kick it up a bit, would be actually build a socket. And so, like the one I'm showing here, that you actually have this device in your kit that you can use to plug into the breadboard, and then take all the 6 wires that you need and wire those to the chip and leave them there. Then what you can do is anytime you want to, you can connect or disconnect this cable just by pulling it on and off. Now, the thing about that little device, it does require some soldering. It's got 6 pins on it, so you have to solder those pins onto a little tiny circuit board, and you can go to M5 and do that. You want to know how to solder anyway, so it's simple soldering. And we bought these and put one of these in your kit. We got it from AVRdude. You can go there and check out their instructions. And if you don't want to do this, it's fine. You can just stick wires into the breadboard. That's fine. But I wanted to show you. I wanted to sort of close out this set of notes with this. This is a picture of one of the printed circuit boards from the Magic Chess game from last year's senior design project. Now, you're a couple years away from senior design project, but in that project, people are doing things with embedded microcontrollers, right? And this is actually a 328p chip on a custom printed circuit board that they made. This is a quad flat package, right? We're using the dual inline package. That's a quad package. You can see that they have their crystal, and then these are the little capacitors, and all of those are soldered onto the custom printed circuit board that they made. Okay? You can see they also have a switch in there and various other things. But I wanted to draw your attention to this ICSP1. That stands for In-Circuit Serial Programming Interface. That connector is there in case they ever want to reprogram the chip. Many, many times when someone builds a professional product like this, of course, this was done by a group of seniors, but they will leave that connector on there so that you can always reconnect the programmer, and you can use that to reprogram the chip if you need to. And that's precisely what this would represent, right? It allows you to put an ICSP in circuit serial programming socket on there. Do that if you want, but you don't need to. It is a little bit of work because you have to go and solder it, but it'll save you a little bit of time from connecting and disconnecting. Okay, that's it for my slides. You'll see all the same thing in the memo that I